It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on a modified state surface approach for constitutive modeling of unsaturated soils was delivered by Professor Xiong Zhang at this workshop. Dr. Xiong Zhang is a professor in the Department of Civil, Architectural, and Environmental Engineering at the Missouri University of Science and Technology. He received his PhD degree in civil engineering from Texas A&M University. Before he joined in the Missouri University of Science and Technology, he worked at the University of Alaska Fairbanks and University of Cincinnati for 10 years. Dr. Zhang has been teaching and conducting research in the field of geotechnical engineering since 1992. His studies focus on development of advanced laboratory techniques to rapidly characterize geomaterials, constitutive modeling coupled hydromechanical behavior of unsaturated soils, numerical modeling of climate-soil structure interaction, slope stability analysis, soil stabilization and ground improvement, and frozen ground engineering. He recently received the 2016 International Innovation Award in Unsaturated Soil Mechanics from TC 106 Committee on Unsaturated Soils within the International Society for Soil Mechanics and Geotechnical Engineering. Dr. Zhang is currently serving as editorial board member of Canadian Geotechnical Journal, associate editor for ASCE Journal of Cold Region Engineering. He also serves as a chair of ASCEGI Shallow Foundation Committee and committee member of several nationwide technical committees such as ASCEGI Committee on Design of Residential Structures on Expansive Soil Standards, ASCEGI Pavement Committee, TRBAFP 60 Committee on Engineering Behavior of Unsaturated Soils, and TRBAFS 20 Committee on Soil and Rock Instrumentation.
Good morning or good evening, everyone, depending upon where you are. So thank you very much for taking the time to attend my presentation. So the topic of my presentation is a modified state surface approach to unsaturated soil study. So this is the outline of the presentation. First, I will give a brief introduction regarding the background of the research, followed by principle of the modified state surface approach, which we proposed recently to investigate the unsaturated soil behavior. After that, I will talk about some applications of the MSSA in terms of explaining existing models, calibrating model parameters, and model expansive and collapsible soils in a unified framework. And after that, I will also extend the modified state surface approach to handle the coupled hydromechanical analysis with consideration of hysteresis. Finally, I will give some conclusions. So before we do the modeling, we need to actually test the soil to get some test results. For saturated soil is easy because the soil has only two phases, soil solids and water. As a result, the volume change of the water is equal to the total volume change of the soil. So normally we put it into triaxial cell, we apply confining pressure and load, and then we measure how much water flow in or flow out of the soil. If we want, we can also measure the port pressure change because the port pressure is always greater than 0. But for unsaturated soils, the testing is a challenge. The reason for this is there are 3 phases: soil solids, water, and air. And then if you apply load to the soil, there will be no water come out, but there is a volume change of the soil. In the meantime, it's very difficult to measure the port pressure because the port pressure is negative and the water can cavitate for port pressure which is less than -100 kPa. So yeah, it's a big challenge. So in 1959, Bishop and his caucus actually developed a new testing apparatus, which is called the suction controlled triaxial test apparatus. So what they did was to actually uh, use a double cell system. The idea is something like this. So for saturated soil, we measure the amount of water flow in or flow out of the soil to get a volume change. But for unsaturated soil, we cannot do it. One idea is maybe we can measure the amount of water between the soil specimen and the cell to use it as volume change of the soil. But the problem is when you apply confining pressure, this cell can deform naturally as a result. The volume change here, what exchange here is not equal to the volume change. So what they did is they use a double cell and then apply the same pressure in the two cells. As a result, the inner cell will not change its shape even if you apply confining pressure. As a result, the amount of water flow in or flow out is the volume change of the unsaturated soils. Also, they replace the bottom porous stone with high L entry desk. The high L entry ceramic desk, its characteristic is when it is saturated, only water can go through it and the air cannot go through it. And then they also supply some air pressure to squeeze the water out of the soil through the high L entry desk. By controlling the difference between air pressure and the water pressure, which is the matrix suction, we can actually control the whole stress path when we do the test for unsaturated soils. So these are the typical stress paths we use to characterize unsaturated soils. So every time because the unsaturated soil behavior is so complicated, so every time we just vary one variables while keeping the other variables constant. For example, the first one is the isotropic compression test and the constant suction. We control the suction, apply all around the pressure to increase the load, and we get the soil response. Of course, we do the test at different suction level. And the second test is the wetting and drying and wetting test at different confining pressure, and we also have shearing test. So these kinds of tests are consolidated drain tests for unsaturated soils. It's very time consuming. Each test takes about 2 to 3 months, and then we need about 20 to 30 tests to fully characterize one soil, and it takes a very long time, normally 3 to 5 years to finish one soil. So even though it is very challenging, but we have been doing testing in the past 60 decades, and now the suction control test has been the standard for the unsaturated soil characterization, and all the existing theory are based upon the results from suction controlled triaxial tests. And yeah, based upon the results from suction controlled triaxial tests, Bishop at the very beginning, a lot of researchers trying to use the effective stress principle for saturated soil and extend it for unsaturated soil to explain unsaturated soil behavior. For example, Bishop proposed the Bishop's effective stress equation for unsaturated soil. But Jennings and Balland in 1962, they found for some compacted fine-graded soil, the soil had experienced expansive soil behavior. For example, when you give wet soil at no confining stress, the volume of the soil will increase. But at a high confining pressure, at a constant load, if we add water to it, the soil can collapse. And the effective stress equation cannot explain the classical soil behavior. As a result, the effective stress equation cannot be used for unsaturated soils. that was the conclusion. And then Matthias and Krishna proposed a state surface approach. They said maybe we need to separate the net normal stress and the suction and then use it to investigate the unsaturated soil behavior. This is called the state surface approach. We use a unique state surface to represent the soil behavior as a function of net normal stress and suction. And then this concept has been strengthened by Ferdinand and his co-workers. And after many years, Dr. Ferdinand and Dr. Rahaju published a book, which is the soil mechanics for unsaturated soils. Because of that, they have Dr. Ferdinand was selected as the 2005 Taisagi lecturer. So this is the development based upon the conventional framework of soil mechanics. And in Europe, Dr. Alonso and his co-workers actually working on the critical state soil mechanics for unsaturated soils. So they published a paper, which we will talk about that. That paper is very famous, and after that, many researchers did propose a model by following the line of the Alonso et al. 1990 paper. So yeah, we will talk about it later as well. So please remember this figure. We will come back to talk about this figure because this is the soil behavior we would like to simulate. So the 1990 paper is actually was developed by Dr. Alonso, Jeans, and Jose. It was the first elastoplastic model for unsaturated soil. It was later called the Barcelona basic model because they have some more advanced version for expansive soil behavior. So the model itself is mainly designed for collapsible soil behavior, and it is the very most cited paper in constitutive modeling of unsaturated soils. And Professor Xiong can say all existing elastoplastic model for unsaturated soils are variants for the Barcelona basic model. So let us have a look at the model. So this is a simple summary of the Barcelona basic model. If you read the paper, you can find it has 6 model components, 13 model parameters, 30 constitutive equations, and if you want to do the calculation, there is 19 calculation steps, which is very complicated. So yeah, if you really want to follow the existing way to do the calculation, this is a good reference, but it's very complicated and I will not have time to talk about it today. So in this presentation, we would like to propose a new approach, which is called a modified surface approach to study the elastoplastic behavior for unsaturated soils. So I have several publications, and I also posted some videos on YouTube. So if you go to YouTube, search the modified surface approach, many of the videos I talked in this presentation is there, so you should be able to find it. So let us start from the simplest test, which is the isotropic compression test at constant suction. So normally we start from a point which is in the elastic zone. We apply load, which will reach a yield point. If we further apply load, we will go along the virgin compression line. If we unload, we will unload along the dotted line to point D prime. If we reload, we will reload to a new yield point, which is slightly different from point V. So normally, in the critical state soil mechanics, this hysteresis slope is neglected. So we just use a straight line to represent it. But we will come back to that. Okay. So if I use a video to represent it, this is what is happening. Sorry. So what's going on? Oh, so yeah, it's here. So let me start from it. So we started from an elastic zone and then goes to the plastic zone, which is virgin compression line. If we unload, we will unload along a line which is roughly parallel to the original elastic segment. If we reload, it will follow the same line until it reach the virgin compression line, the originally reach the maximum stress, and then it will follow the same line. So let me replay this video. As you can see, the test result can be divided into two parts. One is the elastic segment, another is plastic segment. So during this process, loading process, the plastic segment always remains stationary and the elastic segment is movable, but it only moves when there is a plastic loading. It will not move when there is elastic loading or unloading. And the intercept point is always our yield point. Let me replay it again, because this is very important. So as you can see, the virgin compression line actually is the future path of the yield point, right? And yeah, this is the elastic unloading and the reloading during this process. The elastic segment remains unchanged. And then this is plastic loading. The elastic segment will move parallelly downward. So if you can understand this process, you can understand the modified static surface approach. So this is a summary for the modified static surface approach when we only have P loading. So the test result can be separated into two segments. One is the plastic segments. It always remains stationary, and the other is the elastic segment. Segment is movable, but it only moves when there is a plastic loading. It will move parallelly downward. It will not move when there is an elastic loading or unloading. So the intercept point is the yield point. This is very, very important because it tells us the relationship between the yield point and the plastic segment. In fact, the plastic segment is the future path of the yield point. And yeah, so let us go to a little bit more complicated case. For example, we can run the isotropic compression tests at different suction level. So for each suction, actually we have a test results like what we showed previously. So we have a elastic segment and a plastic segment, right? At one suction and then in the next suction level, we can have the same thing. So yeah, if we plot the results in the three-dimensional space of the void ratio versus stress, net normal stress and the suction, you will find the plastic segments are always stationary, has the same shape in a three-dimensional space, right? So if we can run the tests continuously at a different suction level, you can imagine actually the elastic, the plastic segments will become a fixed plus, the plastic segments will become a fixed plastic surface. And then the elastic segments will also become a elastic surface. And the intercept will be not be a point. Instead, it will be a curve, which is the yield curve. So everything two-dimensional becomes three-dimensional, and every thing one-dimensional becomes two-dimensional, right? And then if we apply load, yeah, in the elastic surface, when we apply load, there's no moment of the elastic surface. If we apply load, which reach the yield curve, further loading will cause the soil to stress path to move on the plastic surface, right? The same kinds of concept. So yeah, this is a summary for the modified surface approach when we have the P and the S loadings. So we will have a plastic surface which is always stationary, and we will have an elastic surface which is movable, but it only moves when there is a plastic loading. It will move downward parallelly, and when there is an elastic loading or unloading, it always remains stationary. And the intercept curve for these two surfaces is the yield curve. The yield curve actually, when it moves, the plastic surface actually is the future path of the yield curve, right? So this is the relationship between the yield curve and the plastic surface. And we can keep going by adding the divatoric stress, but the problem becomes more complicated because now the void ratio is a function of P, Q, and S, and I cannot plot it, but we can still have the same concept. So for the triaxial stress state, we also have the modified surface approach. The volume of unsaturated soil becomes a plastic hyposurface. It always remains stationary. We have an elastic surface which is movable, but it only moves when there is a plastic loading, and the intercept now is a surface, which is called the yield surface. And we also have the failure behavior if we have a divatoric stress. It is the critical state line on the hypoplastic surface. So for today's presentation, I will focus on the isotropic condition, and we will only talk about the first three sentences. So the first example I would like to show you the application of the modified surface approach is to use it to explain the Barcelona basic model. So in the paper I published in the Canadian Geotechnical Journal, actually we found in the Barcelona basic model, there are three surfaces are used. One is the elastic surface, which is represented by this figure, which is AFIH, which has an equation like this. And then for the plastic part, it has two surfaces. One is HIJC, which is responsible for the irrecoverable volume change during the drying shrinkage. And then second plastic surface, which is called the JG. This is the surface which is used to represent the unsaturated collapsible soil behavior. And then I used we summarize the Barcelona basic model into the three equations. And if we would like to do the calculation, every time we just need have one variable, which is the C1, which is the intercept of the elastic surface with the void ratio axis, and all the rest are the fixed. So the calculation will be very simple in our paper here. It detailedly explained how to do the calculation, but I want to just show you some videos based upon the calculation. And for all the example in the original Barcelona basic model, we have done a calculation. If you go to the YouTube by searching the modified surface approach, you can find all these videos for each of the example. For example, for case 2, example 2, the soil is originally saturated, and we increase the suction at a no confining stress of 0.15 megapascal, and then we increase the suction from 0 to 0.1, and then we load the soil from 0.15 to 0.6 megapascal, and then after that we will further drying the soil by increasing the suction from 0.1 to 0.2 megapascal. So if you use the modified surface approach, and this is a video which is showing. So initially the soil is saturated, And then we drying the soil by increasing the suction at a constant node. This process is in an elastic zone, so as a result, the elastic surface remain unchanged, the plastic surface remain unchanged. And then we apply load. Once it reach the yield curve, further loading will cause the soil to yield and the elastic surface to move parallelly downward. When it moves parallelly downward, it will form new intercept curve, which is the yield curve with the plastic surface. So this process is called the evolution of the yield curve, and the elastic surface region is always expanding during the plastic loading. So, yeah. So this figure represents the stress path, and which is a projection of the results at the bottom plane as a function of suction and net normal stress. This is the void ratio change as a function of net normal stress. It's the projection of the void ratio on this surface. And then this is the projection of the void ratio as a function of suction on the suction plane. Okay. And then when the suction reach, when the stress reach 0.6 Pascal, if we increase the suction, this is actually an unloading process. The unloading process is an elastic process. As a result, the elastic surface remain unchanged. So this is roughly show the process of how we use the modified surface approach to do the calculation for the Barcelona basic model. You do not need a program. You just need to put the stress path into these three equations, and you will get the results out. And then we did all the calculation. We are able to match all the results in the original Barcelona basic model, except one case, which is the last example for the prediction of Groupies data. So the Groupies data is a very interesting one. And they used two identical soil specimens starting from the same point A. They for one soil specimen, they first dry the soil and then apply load to the soil at a constant suction. And at a constant load, they wet the soil to the original suction level, and then unload the soil to the original stress state. And the second soil specimen, they do a reverse way. They first increase the load at a constant suction, and then increase suction at a constant load, and then reduce the load at a constant suction from C to B, and then wet the soil to its original stress state. So I was able to reproduce the results in the original Barcelona basic model for the stress path of A, B, C, D, A. But we were unable to produce the results from A, D, C, B, A. What we found is there was a small mistake in the original Barcelona basic model. So if I show you the result, you will know what it looks like. So this is the result based upon the modified surface approach. So we apply load to the soil to cause the soil to yield from A to D at constant suction level. So this is the yielding process. And then we increase the suction at constant stress. This is an unloading process based upon the Barcelona basic model. So both the elastic surface and plastic surface remain unchanged. And then after that, we unload at a constant suction, and then reload, wet the soil to its original stress path. So as you can see, even if we come back to the same stress point, the volume cannot recover. So what we found, the mistake made in the original Barcelona basic model is, actually, if you use the conventional way to do the calculation, you need to pay attention to the moments of the LC yield curve and then the SI yield curve. Because in the original Barcelona basic model, now two yield curve, which is the LC yield curve and SI yield curve. The moments of these two yield curve form the two plastic surfaces. And the speed of these two yield curve has to be matched so that we are on the same elastic surface. But in the original paper, I think they have a small mistake when they calculate the coupling effects of these two yield curve. But if you use our method, use the modified surface approach, it's very easy because every time you only need to apply the stress path by finding out what is the location of the elastic surface, you can automatically get the LC and SI yield curve. So it's much, much simpler to do the calculation. So this is one benefit of the modified surface approach. It makes your calculation process much, much simpler. Okay. So that even, actually I have been teaching this method to master students for many years. They have no problem in reproducing the results in the Alonso et al. 1990 paper. So you may ask, why do we need the modified surface approach? Of course, you proposed a new way to actually simplify the explanation of the Barcelona basic model, but what's your contribution? So here I will show you an example why we need a modified surface approach. For example, in 2004, European Union actually funded a project which is called the MUSE Research Training Network. And one of the tasks for the MUSE Research Training Network is to benchmark the calibration of the constitutive model for unsaturated soils. So what they did was to provide 7 universities with the same sets of experimental results. Now asked to calibrate, they're asked to use the same model, which is the Barcelona basic model, and then they're asked to use the same test results to calibrate the same model parameters. Now allowed to use any method, and the expected results should be the same or at least to be very close, right? But in fact, as you can see, this is what I took from their paper. What you can find is actually the calibrated results are significantly different. For some model parameters, the difference is 10 to the power of 7. So what's the problem? So in that exercise, in fact, researchers used 2 different approaches. One is what they call the sequential approach. Another is called a global optimization. So to make my explanation clear, I would like to give you a simple example. For example, if we would like to fit a plane by using some experimental data. For example, my model is a plane, and then this is my test results. I have 4 points. AB is on a straight line, which is at the XOZ plane, which is has the equation of z is equal to 3 minus x, straight line. And the CD is on the YOZ plane, and it has the equation of 2.5 minus 2y. And if I need fit the plane, actually, this is the plane I will be able to fit. This is the equation we have. So if we need to do the calibration of the model parameters by using this data, we can do a sequential approach. In a sequential approach, what people normally do is you use the first 2 points, A, B, and fit it with a straight line. And then you get the slope A, which is -1 here. And then the second step, you use point CD to fit a line, you get the slope -2 as a B. And then you're trying to combine these two results as the model parameters to for this plane. Obviously, this is not right. The reason for this is for the first regression process, we just use the partial test results of AB to do a partial burst fit for the model parameters. And it's the best fit for point A and B, but it's not the best fit for the overall results. The same thing happened for C and D. So even though for each regression we have 100% of R square, but the overall R square is very low. If you look at here, it's 0.6. And if we would like to do a global optimization, which is normally we do using the incremental formulation, we just take the complete derivative of the analytical solution to have incremental formulation like this. And then we select the initial point, any of the initial point, and then calculate the dz, dx, dy, and then try to optimize to get the model parameters A and B. This is not good either, because every time you have to select the initial point. By doing so, you assume the point has the correct answer, is exactly on the best fit plane, but this is not the case. As a result, depending upon which point you are choosing, you will not get the same results, and the result you get is not correct. Obviously, the best way to do the calibration of this model is to use the analytical solution to best fit all the test results one time to get the best fit for the whole model, right? So this is simple and it's clear, but you might not realize that in the past, at present, actually all of us are doing the sequential and the global optimization. The reason for this is all of our existing models are proposed based upon the incremental formulation, based upon the slopes. For example, this is a summary of what we have for the Barcelona-based model, 3 equations, right? But if you look at the original Barcelona-based model paper, you can find the original Barcelona-based model was proposed by first proposed the slope of the void ratio versus of the applied net normal stress. They proposed that log linear equation with a slope of kappa, right? And then they also proposed another incremental formulation, which is the void ratio change as a function of suction inside the elastic zone. They have a slope of kappa sub s. So it is two, actually, the slopes, the equivalent model for the Barcelona is the equation plane like this. If you take a partial derivative of this equation, you can get these two slopes, partial derivatives, right? So this is what they proposed for the elastic part. So they also proposed the part when there is drying shrinkage and when there is irrecoverable volume change. So they proposed a log linear line, which is lambda sub s, right? And also they proposed a horizontal SI yield curve. By doing so, actually, it is equivalent to say in the plastic surface here, when you apply load, the net normal stress, the volume change has a log linear relationship, which is the same as the kappa, which is in the elastic zone. And yeah, this is how this surface is formed, right? And then for the collapsible soil behavior, what they proposed is to first propose a log linear relationship for the normal compression line with a lambda sub s. And then they also proposed a shape of the LC yield curve. By doing so, it's equivalent to propose a partial derivative of void ratio as a suck versus suction of this. This is very, very complicated, right? And then after they have all the partial derivatives, they try to combine all this model together to form the Barcelona basic model. So yeah, this is actually not the best way to do it. So if you look at the form and the surface, it is quite different from the test results we have obtained for compacted soil by Jennings and Ballant, right? The original one. So yeah. And then it also caused a lot of problem for the model parameter calibrations, right? Because the model is proposed in the incremental formulation. So every time we try to calibrate kappa sub s, lambda sub s, lambda s, and then after that we try to combine them together to form a constitutive model for unsaturated soil. From the previous example, you can clearly see this is not working, right? But if you use our method, I can show you actually the model calibration for unsaturated soil is very easy because we have the closed form solution. We can just use the test results and the best fit these equations, and then we can get the results. So yeah, I can show you another example, which including both the model parameter calibration and the determination of the yield curve. So yeah, there's an argument in terms of what is the, actually, the LC yield curve is well accepted, its shape, but there's an argument for the SI yield curve. So many researchers has proposed different kinds of the yield curve shape for the SI yield curve. So at the present, this is how we determine the LC yield curve. We will run a lot of isotropic compression tests at constant suction level, and we have some test results like this. And then by using the constant grinding method, we can find the yield point. For example, for each test, we will plot in the P versus S stress path space, and then we connect the yield points to get the yield curve. So this method is straightforward, but it requires all the soil specimen has the same stress history so that all the yield point is on the same yield curve. But in reality, it's very difficult to get identical soil specimens. And then if the soil specimen does not have the same stress history, for example, yeah, for the second soil specimen, this is its yield curve, and for the third soil specimen, this is its yield curve. When you run the tests for the isotropic compression, you can still get the similar shape of the specific volume versus the P curve. And then you can still find the yield points, but you will not know if they are on the same yield curve or not. If they are not on the same yield curve and you collect them, it's a wrong result, right? So some researchers also use the similar method to determine the SI yield curve by running the drying and wetting tests at the constant load, and then determine the yield points, and then connect them to get the yield curve. So this is exactly what is done in the Xu et al. 2007. But it also requires all the soil specimen has the same stress history. But if the soil has a different stress history, then even if the soil have a horizontal SI yield curve, if you run the test, you can still using the existing method to analyze the SI yield curve, you can get a curve like this, right? So the existing method is not good if you use soil specimen with different stress histories. But if you use our method, it will be quite simple. For example, these are the test results we obtained from Su et al. 2007 for a bunch of isotropic compression tests at different suction level. These are the test results. And we can get the yield points by using the constant gradient method. So what you need to do is to plot all the results in three-dimensional case, and then you separate name. From the yield point, you have the elastic segment and the plastic segment. It doesn't matter if the plastic segments are, it doesn't matter if the soil specimen have the same stress history, because all these plastic segments will be on the plastic surface, right? So for example, BC, VF, XI will always be on the plastic surface. So as a result, it will be very easy for us to actually to use only the plastic segments to fit the Barcelona-based model to get its plastic surface. And then we know the elastic surface, so we can also do a regression for the elastic surface. Once we have the elastic surface and the plastic surface, by intercept the elastic surface with the plastic surface, we can have the yield curve. So we can actually change the C1 by moving it down. We can get all the LC yield curve. It's that simple. And then if you need to develop your own model, if you do not want to use the Barcelona-based model, you can simply use these test results to propose, to fit any functions you, equations you like, so that you have your own new model. For example, for the Groupies data, this is the original Barcelona prediction, but in our paper, we use the plane to fit the same data. Actually, we found with a simpler model, we can get a better modeling results. So it's very easy to use the modified surface approach to develop new model as well. So yeah, so let's go back to this story. So for this test results, by doing so, actually we can find the yield curve for net soil. For example, the red solid lines represent, for this line is the results from the Su et al. For the LC yield curve, and this is the red curve is the SI yield curve from Su et al. But the black lines are the yield curve we got from the modified surface approach. For example, for this part, the LC yield curve is the same as Barcelona-based model, but for this part is different. So what we found is actually in the Su et al., actually when they ran the test, actually they change the stress history of the soil. For example, if I would like to run a test for the drying and the wetting test for this one, in order to do the test, if I have a soil specimen which is initially saturated, I will have to apply load to a stress of 200 kPa, and then I will do the drying and the wetting test. So during this process, if I load the soil from 0 to 200, I have already yielded the soil in order to be able to run the test, right? So even if all the soil specimen at the very beginning has the same stress history, but the preparation process will change the location of the yield curve and cause different stress history. So yeah, again, we found that the yield curve, this part is the same as the Barcelona-based model, but for this part is different. Originally, yield curve like this is considered as illogical, but we found actually this kinds of yield curve is very useful to explain expansive soil behavior. Remember at the very beginning, most of the compacted soil are expansive at the low confining stress level and becomes collapsible soil behavior at the high stress level, right? This is exactly the yield curve we need to simulate the expansive and collapsible soil in a unified framework. So if you have these kinds of yield curve, actually it's corresponding to the steady surface like this. At a low confining stress, the soil is expansive. If you add the water to the soil will be swelling. And then if at a high stress level, if you add water to the soil, it will collapse. For example, in our second paper of the modified surface approach, we showed if you start from a point A, which is when the soil is dry, apply load to point C at low stress level. If you wet the soil will increase in volume, which is from C to D. But if you apply load from C to A to C to E to a high stress level, if you wet the soil, actually the volume of the soil will decrease from E to F. I will show you a video so that you can see how the yield curve is changing. So initially, the yield curve is in the elastic zone, is in the expansive soil zone, right? And then if we add water to it, it will have swelling. But if we keep loading the soil, the shape of the yield curve will change into the Barcelona basic model type, and then it will cause collapse. So let us do the modeling again. So this is a three-dimensional case. This is for the unsaturated part. This is for the saturated part. So this is the expansive soil behavior, and the loading caused the yielding of the soil, change it into the collapsible soil behavior. Okay, so that by doing so, actually we can simulate both expansive soil and collapsible soil in a unified framework. And we also did some kinds of extension for the modified surface approach to model the coupled hydromechanical stress behavior. Because in the original Barcelona-based model, they only have the elastoplastic model for the volume change part. For the hydronic part, they do not have a elastoplastic model. So yeah, what we found is if you have a constant suction loading curve, for example, if we load the soil from A to B and unload to C, of course, B is the yield point because we have irrecoverable volume change. So this is for value ratio, and for the water content, the yield point is at the same location, and for the degree of saturation is at the same location. So this is for consolidated drained test. For undrained test, for example, a constant water content test, if we apply load from A to B, which reach the initial yield curve and keep loading in undrained container to C and unload, what we found is point C is the yield point, is the same for the void ratio and the degree of saturation. So as a result, we conclude for both the volume change and the hydronic part, they always share the same yield point. So we added this component to the modified data surface approach to model the coupled behavior. You only need one sentence, which is the degree of saturation, void ratio, and water content actually share the same projection of the yield point or yield curve in the PS space. By doing so, actually we can model a coupled hydromechanical behavior for unsaturated soils. For example, this is a simulation for suction controlled test. So the upper part represents the volume change behavior, and the lower part represents the water content change behavior. The yield curve on the two surfaces is different, but their projection at the bottom plane is the same. is the same. And then this make the model very simple because you only have one yield curve, but you can model a lot of behavior for unsaturated soils, right? This is constant suction loading, and we also have the undrained loading, right? So this is the void ratio surface. This is the water content surface. We have a constant water content loading, and during this process, they share the same yield curve. Water content is not changing, and the void ratio has zero recover volume change. So this situation is for the coupled case. But in the real soil behavior, actually, when you load the soil and unload, then there's a hysteresis. If you just apply load and unloading at a constant sucking level, or if you wet or dry the soil, drying or wet the soil at a constant load, you also have hysteresis. So these kinds of behavior cannot be simulated by existing model. So we also added the components to the modified state surface approach to handle the hysteresis. So what you can find is, if we go back to the one-dimensional case for the P loading, so we started from point in the elastic zone, reached the yield point, fed load to point V. If we unload, we have a unloading curve, VD prime. If we reload from D prime, we have a new yield point. So these 2 points will not be the same. And if we need simulate a hysteresis process, we need to have a new unloading curve and a reloading curve. But what is common is, in the end, the yield point is always on the same virgin compression line, right? So what you need to do is just a new reloading surface, right? So yeah, this is the modified surface approach with consideration of the hysteresis. You need a unloading surface which is different from the reloading surface. And the 2 surfaces are movable, but it only moves when there is plastic loading, and it will not move when there is unloading or reloading. And the plastic surface is always stationary, and the intercept curve is always, the yield curve is the same, because they always go back to the same normal compression line, right? So if I show you one example, this is what it looks like. Yeah, remember, so this is unloading and reloading. When there's unloading, the unloading surface will remain unchanged. When there's reloading, the reloading surface will remain unchanged. But both surfaces have an intercept curve with the plastic surface. So they share the same shape, but only with different kinds of stress history. In this way, it makes the modeling very simple, and you always have the same yield curve. And you can model the hysteresis behavior for void ratio and water content simultaneously. So this is my conclusion. We proposed a modified surface approach to simulate the unsaturated soil behavior. It bridges the gap between the original surface approach and the existing elastoplastic theory for unsaturated soils. It provides actually integrated form, closed form solution for a constitutive model. It established a relationship between the yield curve and virgin compression lines. Actually, they are the same. And then it can be used for many applications and model expansive and collapsible soil behavior in a unified framework. And it has many advantages over the existing incremental formulation. And it can be easily extended to model coupled hydromechanical behavior for unsaturated soils. So here are some of the reference I used in this presentation. And thank you very much for your attention. And I'm happy to take any questions if you have. Actually, this is a very good question. I will come back to my original position. Yeah, the benefit of the modified surface approach is actually it does not require you to accurately predict the yield point. So I know normally we use the constant gradient method to predict, to estimate the yield points, right? But most of the time they are not accurate, right? Because it's an empirical method. But if you use our method, you do not have to have an accurate prediction of the yield point. For example, if for this segment, for the second test, if you are not confident to say V is the yield point, what you can do is you can select a value is large enough so that you are comfortable to say, oh, this is for sure is on the normal compression line. So that you just use a smaller segment from, for example, from this point to F and use it to do the regression to fit your model. And you can still get the plastic surface. And after you get the plastic surface and the elastic surface, you will have a very good feeling to say if V is on the plastic surface or not. Does this make sense? So you do not need have an accurate prediction of the yield point if you use our method. I don't think so. I don't think so. Normally, the yield stress will increase, always increase, right? If you apply load, it will always increase to a higher value, right? So it will not come back, of course. For some situations, if you in the future, if you want to simulate a situation, you might need a new framework. But I do not think in the current critical state soil mechanics or in the generalized plasticity, we can allow this to happen. You have many ways to do so because remember you have a closed form solution. It really depending upon how confident you are with the model. So normally if you are confident with your test results, then the next question is you can select different equations to best fit the data so that you can have the best model, which is I have shown here, right? And then another possibility is you are very confident with your model. You think, oh, this is a very good model which can represent the soil behavior well, but for the soil test, you have less confidence. Then what you can do is you can use a method which is called the Ransack method, which is actually, if you assume the model is correct, actually it can, if you use Ransack method, it can automatically filter the wrong data and only use the correct data to best fit your model. So these are two different scenarios you can consider.